So, developmental trauma and the immune system. How trauma impacts stress systems and your lifelong health. How do early life experiences impact your immune system? This video will explain how developmental trauma changes stress regulation, specifically the balance between the cholinergic and adrenergic systems, and why that leads to chronic inflammation, elevated IL-6 cytokines, and a greater risk of autoimmune disorders. Don't worry, we'll break this down. We're exploring how trauma in childhood links to two big health outcomes, heart disease and autoimmune disorders, and how that involves two key body systems, the HPA axis, which is our stress hormone pathway, and the vagus nerve, which helps calm our body and regulate inflammation. Adverse childhood experiences, also known as developmental trauma, are increasingly recognized as powerful determinants of adult health. Emerging research shows that early stress can alter the regulation of our autonomic nervous system and the hypothalamic pituitary adrenal axis, also known as the HPA axis. This and immune responses increases the risk for cardiovascular disease and autoimmune conditions decades later. Developmental trauma refers to the chronic stress or neglect during sensitive periods of childhood brain and body development. Examples include ongoing abuse, neglect, and unstable caregiving environments. Because neural circuits are still forming during childhood, persistent stress can recalibrate how the brain and body manage threats, establishing long-term patterns of heightened vigilance and altered stress regulation. Developmental trauma changes how our nervous system works. So, two main systems are involved in the nervous system. The parasympathetic branch includes the vagus nerve and uses acetylcholine, and the sympathetic branch, which uses adrenaline and norepinephrine. Less vagal activity means more inflammation. In trauma survivors, parasympathetic or vagal activity is often reduced, while sympathetic or adrenergic activity is chronically high. This imbalance alters immune control. What helps me remember the difference between cholinergic and adrenergic systems is that cholinergic is parasympathetic, which is known for allowing us to rest and digest, and colon sounds like the first part of cholinergic. Adrenergic, I remember, is sympathetic because adrenaline kind of sounds like the beginning of adrenergic, adrenaline, sympathetic, cholinergic, colon, parasympathetic. And onto the interleukins. Interleukins are chemical messengers. We think of them as text messages that immune cells send to coordinate responses. There are over 30 of them. Each has its own job. For example, IL-1 sparks fever, IL-2 activates immune soldiers called T cells, IL-6 ramps up inflammation, and IL-10 helps calm everything down once the threat is over. Trauma, especially in childhood, often raises IL-6, a pro-inflammatory signal, but it lowers anti-inflammatory ones like IL-10. This leaves the body stuck in a constant attack mode, which increases long-term risk for chronic inflammation and autoimmune diseases. On the other side, the sympathetic or adrenergic system drives fight-or-flight responses. When it's overactive, it triggers more immune cell activity and increases inflammatory signals like IL-6. High IL-6 is one of the strongest biomarkers linking stress to autoimmune disorders. Some survivors have higher resting IL-6 decades later. In children experiencing chronic trauma, cortisol levels surge too frequently, and over time, the system can become dysregulated. Some adults end up with chronically high cortisol, increasing blood pressure and abdominal fat and inflammation. But some others feature the opposite, like extremely low cortisol, and that indicates that the body has burned out all of its stress response. The vagus nerve is like the body's internal brake system. It slows your heart rate to calm down stress responses and regulates immune reactions. It helps the body shift out of sympathetic and return to parasympathetic after a stressor is over. When the vagal brake is engaged, it slows the heart rate, promoting a sense of calm and safety, but its release on the brake allows for increased heart rate and mobilization, otherwise sympathetic. Now onto the HPA axis. The HPA axis is short for hypothalamic pituitary adrenal axis. It's your body's main hormonal stress pathway. It starts in the brain's hypothalamus and sends signals down to the adrenal cortex on top of your kidneys to release cortisol. Cortisol's effects linger in the body way longer than, say, adrenaline or noradrenaline. The adrenal medulla is the inner part of the adrenal gland below the adrenal cortex. It's not part of the HPA axis, but it's still relevant here because it releases the adrenaline and noradrenaline, and these hormones initiate the immediate fight or flight response to stress. They go down pretty fast after the threat is perceived as gone, whereas cortisol seems to stick around for quite a while. While the adrenal medulla is not part of the HPA axis, it's activated during stress alongside the HPA axis. The HPA axis and the adrenal medulla's release of adrenaline and noradrenaline work together to prepare the body for a stressor. The HPA axis, with its slower cortisol-driven response, helps sustain the effects of the initial adrenaline rush. Trauma often lowers what's called vagal tone, meaning your ability to activate this calming response is weaker, and that's why many trauma survivors have a faster resting heart rate, a lower heart rate variability, and a higher baseline stress, even when nothing stressful is happening. This is known as heart rate variability. You want a big window of heart rate variability. Trauma survivors tend to have a very narrow window. Heart rate variability doesn't vary enough in trauma survivors. It stays relatively the same across situations. The vagus nerve controls inflammation through the cholinergic anti-inflammatory pathway, or parasympathetic. When active, it releases acetylcholine, which binds to immune cells and reduces pro-inflammatory cytokines like interleukin-6. When vagal tone is low, the vagal brake is weakened, and it's less effective at initiating the anti-inflammatory parasympathetic response after a threat. Without a good vagal brake, the inflammation from stress, like IL-6, is harder to reverse afterward. IL-10 and increasing IL-6, it makes it harder to reverse the stress response afterwards and return to parasympathetic. Opposite of the cholinergic parasympathetic system is the sympathetic adrenergic system, which drives fight or flight responses. When the adrenergic system, or the sympathetic system, is overactive, it triggers more immune cell activity and increases the inflammatory signals like interleukin-6. High IL-6 is one of the strongest biomarkers linking stress to autoimmune disorders. Studies, including the 2024 Brain Behavior and Immunity Review, show that trauma survivors have a higher resting IL-6 decades later. The combination of low cholinergic control and the high adrenergic drive in trauma survivors creates chronic low-grade inflammation. It puts a dent in the immune tolerance and opens the door for autoimmune conditions like rheumatoid arthritis, lupus, multiple sclerosis, and Hashimoto's thyroiditis. Population studies show that individuals with 4 or more ACEs, that's adverse childhood experiences, are 2 to 3 times more likely to develop autoimmune diseases than those with none. Considering all of this, how does trauma end up as heart disease? Well, when cortisol is constantly high and the vagus nerve isn't balancing things out, your blood pressure climbs, blood sugar regulation worsens, and the inflammation quietly damages your blood vessels by stretching them out. Over the years, this leads to plaque buildup or atherosclerosis, making heart attacks and strokes more likely. A 2022 study by Jackson and colleagues found that adults who had multiple adverse childhood experiences were over 2 times more likely to develop coronary heart disease, even when lifestyle changes like smoking and diet were controlled for. The sympathetic or adrenergic system stays overactive in trauma, releasing adrenaline and noradrenaline, raising inflammatory cytokines like interleukin-6, keeping inflammation elevated long after the stress has passed. The same stress systems also influence the immune system. Normally, cortisol suppresses excessive inflammation, but in many trauma survivors, the body becomes resistant to cortisol signals, so inflammation goes unchecked. Combine that with low vagal tone, and you've got a recipe for an overactive immune system. This chronic low-grade inflammation can eventually cause the immune system to start attacking its own tissues, which is what happens in autoimmune disorders. That includes rheumatoid arthritis, lupus, Hashimoto's thyroiditis, multiple sclerosis, and some others. Large population studies, including a 2024 meta-analysis by Lopez Olivo and colleagues, show that people with 4 or more ACEs are about 2 to 3 times more likely to develop an autoimmune disorder than those with no childhood trauma. Trauma isn't just psychological. It can actually change how our genes work through something called epigenetic modification. Trauma can alter stress-related gene expression and the gut microbiome. Both of these influence immune function and inflammation. Early adversity can literally program the body to respond to stress and inflammation differently for decades to come. Epigenetics add tags like methyl groups or modify histones to control gene expression. Trauma and chronic stress often lead to a less diverse gut microbiome. That diversity normally helps regulate immunity and protect against inflammation. When it's reduced, the gut can become more vulnerable to harmful bacteria and immune dysregulation. Stress hormones like cortisol and noradrenaline can actually change the gut environment, favoring bacteria that produce pro-inflammatory molecules like lipopolysaccharides.
This can increase gut permeability, sometimes called leaky gut, allowing inflammatory molecules to leak into the bloodstream. On top of that, trauma has been linked to lower levels of helpful bacteria like lactobacillus and bifidobacterium. These bacteria normally produce short-chain fatty acids, which help maintain gut lining health. This reduces inflammation and influences brain function through the gut-brain axis.
Vagal activity and IL-6 reduction are possible. Trauma-informed therapy alongside mind-body practices like yoga and meditation, slow breathing, and improve vagal tone. They can lower inflammation and improve your heart health. Social support and safe relationships also help reset the nervous system by instilling secure attachment pattern across relationships over time.